My name is Jiahao Chen. Until about 4 months ago, I was at MIT CSAIL with the Julia Labs. I currently work at Capital One in New York, but the disclaimer here is that this is all work that was done before I went to Capital One, so they don't get to tell me what I can't say about this topic. So some of you may remember this issue, taking back the Transposes seriously. How many of you have read this issue? Oh my goodness, okay. All right. 3/4 of you guys raised your hands, okay? So the punchline here is that we were wrong on at least 4 counts on this issue, and I will explain as much as possible within half an hour why we were wrong. As you know, 4774 is quite possibly one of the most hotly debated issues of our time, and I went to sample some luminaries of our community to ask about their opinions. So here's one. Oh, sorry, thank you. So here's one opinion. Here's another opinion from another luminary. And here's yet another opinion from another luminary, who unfortunately could not be here, and thus was born this issue. Surprisingly, it's not just us. So turns out that the Python people had also thought about this, and they had, 381 comments on this particular issue. So this seems to be something that gets people riled up a lot. So let me introduce the surface problem. This is what Julia 0.6 looked like. So here, I Googled the first image for mathematician, and that is what I got. So I'm using that. So user comes in and says, I can't compute with Julia. I typed this, and it gave me a 1-element array. And then I tried to put it in a more complicated expression, which I want to type, and it says, blah, 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 error, sad. I am unhappy. Don't you know any mathematics? Oh, it's still cut off, huh? It says, don't you Julia people know any mathematics at the bottom? Our response here is, why would you want to do that? Okay, why do people want to write inner products like this? And why do people get so worked up about this issue? So I did some research. And I've come to a conclusion that people don't know what vectors are. This issue exists because there are 2 slightly incompatible meanings of the word vector in mathematics. Here are the 2 definitions. A vector is a column of a matrix. Second definition, a vector is that which has the algebra of a vector space. Not meant to be fortuitous tautology. Naturally isomorphic but not identical. These 2 vectors are similar but not identical. So a type 1 vector, a column of a matrix, clearly has the algebra of a vector space. However, not all vectors which have the algebra of a vector space are columns of matrices. On some level, this issue really is that simple. And I will refer to these 2 vectors as column vectors and flat vectors for the rest of this talk. I will be careful where possible to distinguish between these 2 uses of vector. But you might ask, why did we end up with 2 definitions of vector anyway? And it turns out, I read some books, and it turns out that this is what the history of linear algebra looks like. And this is as simple as I've been able to make it. In short, sometime around 1924 to 1960, there was a division in the historical treatment of matrices and vectors. There was once a universe where matrices were their own subject and vectors were their own subject, and these 2 subjects did not mix whatsoever. And at some point, they merged. And we work in the world of the post-merger universe of matrices and vectors. Just some key moments in the history here. So we see that on the left-hand side, the matrix-only universe, we have things like phrases like column matrix. We have the notation that many of us recognize today when we do linear algebra. On the vector side, we have the vector space axioms, we have the coordinate geometry, we have the notion of tuple. And at some point in the 1920s, the mathematicians said, oh, hey, column matrices form a vector space. And hence was born the other definition, which is both older and newer than the other definition. So if this is too complicated, I have tried to retell the story with emoji. There's a pre-unification era. There's the early unification era, where you needed to explain this carefully. And then there's the era where it's also obvious you should have learned this in elementary school. So what does this look like? So I pulled out one of these books, and Van der Waarden's book on modern algebra is arguably the textbook that invented abstract algebra in its modern form. And what did he write about this? You will notice, first of all, that this is all not in German. It's in English. But nonetheless, you can, I have it on good authority that this survives from the first edition of the modern algebra textbook. That this is how he named all the things. So vectors were the abstract thing that had the algebra, and it is composed of coefficients, and the coefficients themselves form tuples. And by the way, you can assign to this vector a column matrix. So to recap, the algebra is in the vector. The coefficients, which what we may today call ring elements, are just some numbers, some scalars. These are the things that define scalars. Tuples are indexable collections of these coefficients, these elements of a ring, but there's no algebra defined on them. And then, by the way, there's this older topic called linear algebra that has column matrix. Warning again, most of these words are horribly, horribly overloaded. But I think this maybe gives you a sense of what mathematicians were thinking about when they talked about algebra and vectors and in the context of vector spaces. Another book that I thought was really enlightening about this era comes from this book, which has this awesome title called The Vectors of Mind. Multiple factor analysis for the isolation of primary traits. So this is actually a statistics textbook from 1935, and I think it explains very clearly how this evolution made a transition from the isolated universe to the post-unification universe. So I will read a little bit of this. Basically, that if a matrix has a single column, it is a column vector. If it has a single row, it is a row vector. And the vectorial terminology probably can be regarded as a consequence of geometry. So I think this is really, really the crux of the matter. Fast forward to 1953, when the field of numerical analysis was invented. And this is the language and cornerstone of how all numerical analysts today speak matrix algebra. So most of you here may not be familiar with householder notation, so I will just summarize this very briefly. Essentially, there is a typographic convention where scalars are small Greek letters, vectors are small Roman letters, and matrices are large Roman letters. And you want to spell certain things as follows. For example, you might want an inner product, which you want to write as u prime times v, an outer product that's u times v prime, and then you have bilinear forms that look like u prime times a times v. And I would argue that just about every complicated expression involving matrices and vectors really come down to compositions of these elementary types of products. Now, the interesting thing here is that you only need two operations to express all of them. You only need the transpose and the multiplication. Okay, and there's a caveat here. Oh, excuse me. Let me try that again. Okay, sorry about that. So the caveat here is what exactly we mean by transpose and multiply. So let's dig into one of these things. It turns out that there is an assumption here about matrix algebra that is hidden in the desire to write something like u prime times v being a product involving vectors and vectors, returning a scalar. So I've tried to break it down in the way a computer scientist might, and try to assign the meanings of various arrows here. So you see that what you do here is, first of all, you convert everything to matrices, and then the regular definitions of matrix transpose and matrix multiply automatically hold. You don't need new definitions of what prime and star are in this case, so long as you are able to automatically convert between vectors and column matrices on the left-hand side, and on the right-hand side, a conversion between one-by-one matrices and true scalars, which are these coefficients of the field. So what's really missing here from this picture, which I will highlight explicitly, are these isomorphisms. And this is really, it comes down to the crux really of whether or not you want your language to deal with these isomorphisms for you, or whether you want to deal with them yourself. All right, that's the second version of the punchline. Julia, prior to 0.6, actually used this particular definition. So in the context of an inner product, what we said was, the promotion from vector to matrix and matrix transpose is our definition of what a vector transpose is. And the thing that results from this is that if you think about this expression as the composition of just transpose and multiply, that it's actually broken. And it's broken in a very bad way, because this is what happens inside in Julia 0.5 and earlier, that you promote the left-hand side vector to a matrix, then apply a transposition to get a row matrix, and then you have a matrix vector product, which of course must return you a vector. And vectors are bad because you cannot divide by them. They don't have a scalar algebra. For example, that one-by-one matrices are actually much better at. You can do scalar operations with one-by-one matrices, and you just can't do very much with one vectors. And the result is unhappy Einstein. So this other competing language that you may have heard about, MATLAB, I will argue that MATLAB is an anomaly in modern languages, and it's why we feel uncomfortable about some of its semantics. And it's because it's firmly rooted in type 1 vectors, which are columns. So 2 quotes from various documentation about MATLAB. The first one comes from the original matrix laboratory report from 1980 from the University of New Mexico, when Cleve Moeller was still faculty there. In MATLAB, the matrix is the only data type, with scalars, vectors, and text as special cases. The second one comes from last year's MATLAB manual, where it still says matrices with dimension equal to 1 on one side and e greater than 1 on the other side are called vectors. So now that we are primed to see that there are 2 definitions of vector, this is very clearly a type 1 vector that is being defined in MATLAB. So why doesn't MATLAB have this problem? It's because everything is a matrix, and everything is coerced on demand to a vector or scalar as necessary. And some of you may know this as the trailing singleton dimension rule, where you can arbitrarily add or remove extra dimensions that have just length 1 at the end of a array in MATLAB. So what you see here is that our isomorphisms simply become the addition and dropping of trailing indices as necessary. And furthermore, in MATLAB, you just stop at the 1-by-1 matrix expression. You don't need to convert it to a true scalar, because that's good enough. And so this actually is a fairly elegant solution to the type 1 vector implementation. Why is this bad? It's not necessarily bad, but it's not really in line with how we think about dispatch, because now you have to add these definitions to multiply that are shape-based. So you have to special case 1-by-1 matrices on the left and 1-by-1 matrices on the right in order to get this to work the way you want it to. So to summarize, language design considerations, if you want to rely on just transpose and multiplication to write these expressions, you probably have to define transpose and multiply very carefully. And otherwise, you probably need special parsing rules just to make this happen. Effectively, you're making something like blank prime star blank is really its own special operator. And this breaks composition, which may be very, very bad. If you think about accidentally introducing parentheses in the wrong place, you may get the wrong type as the result. And these kinds of special parsing rules, as people like Jeff, I'm sure, will tell you, they add complexity to a language. And this is complexity for a very specific purpose, and it seems a little odd to do this. So what is the design space here? And it turns out that there are really only these 2-by-2 choices. If you only have scalars, matrices, and vectors in your language, then these are the 2-by-2 matrix, as it were, of the design choices. You can either have A times B produce you a vector or a column matrix on the one end, and on the other hand, you can define the transpose of a vector to return you a row matrix or just itself. And so this is what you get wrong if you want to insist on implementing householder notation. That in some quadrants you get inner product wrong, which is us in old Julia. In another quadrant you get outer product wrong, and the quadratic products and bilinear forms are wrong on the other side. So that's our main result here, that you can't have what you want. Thus was introduced the row vector, and it turns out that having a row vector combined with the type-based dispatch that we know have grown to love in Julia actually can get everything to work. So the moral of the story is that you can't get what you want for householder with 3 types, but you can with 4. So what did everyone else do? And this is a really interesting slide, I think. I've gone through and looked at what other people do in this case. You can see that there's a wide variety of things you might do to vector transpose. Either it's an error, like in Lua. It can be the identity, like in NumPy, in Mathematica, and also in SciRuby. We have the old Julia behavior on one hand, and we also have the new Julia behavior in yet another box. And it turns out that we're not alone in this box. There is this other language called PariGP, which is used in number theory calculations, which actually has this design. And furthermore, you have to explicitly convert between columns and matrices, and rows and matrices, and rows and columns. On the other hand, there's R, and R is actually a really interesting design quadrant here, because basically, the moment you do any linear algebra, the result is a matrix. So on some level, this is actually really easy to understand, because once you invoke the matrix multiply operator or the transpose operator, you get a matrix. And arguably, MATLAB sort of fits in this corner, but not really, since we've already discussed that MATLAB does not have true scalars or vectors. And then there are these little pieces here that nobody's explored, and maybe this is an avenue for new language design. So if you were interested in making your own language, you might want to try these out for yourself to see how you like them. So how do row vectors work? We need new definitions of transpose and multiply, but then the actual expressions that you get is simpler, because all you do is just apply those two new definitions, and then you're done. So the question is this really that bad that we need more definitions? Probably not, because as you know, multiplication is already highly polymorphic in Julia. Just for the record, everything past the first method definition is font size 1.5. Right? That's how many methods we have in Julia. But in some sense, this is a very natural. There's a very natural analogy between how Julia organizes this kind of generic function system and how we learn how to do mathematics. So I don't think anyone really learned multiplication from complex numbers. I think all of us started from multiplication tables, which is int times int. Then maybe you graduate in school to go to fractions, and so you have rational times int. And then maybe you have real numbers and decimals, then you have real times real. Then if you stay in school long enough to learn more mathematics, you learn complex times complex, matrix times vector, and all this other fun stuff. So really just introducing new things like row vector times matrix, row vector times column vector is just more of the same. So that's a little bit of a hand-wavy justification for why this is not such a bad design. So the current, excuse me, we don't really need the slide. Instead, I will skip forward to just the summary, and I'll leave plenty of time for questions. I'm sure you have many. First of all, I think we have taken vector transposers seriously at this point. And really, special credit really has to go to Andy Ferris, who is here somewhere, right? Where are you? Please give this man a warm hand. As you know, it was my privilege as an academic to just speculate about what to do, but Andy actually did it, so that also deserves plenty of credit. So really, what I've learned from this is that we were all wrong about vectors, and we have forgotten what used to be difficult. We've forgotten that we used to have to worry about these isomorphisms explicitly. We have this incompatible definitions of columns, of column vectors and flat vectors. We've forgotten that multiplication is actually this inherently overloaded and polymorphic operation. And one new result here is that you need at least 4 types to do householder notation in a type-based dispatch system. And I will leave it at here and take any questions you may have. Thank you very much.